good morning and thank you. It's wonderful to see you, except I can't actually see you. You are like a sea of darkness out there. But I hope that you can see me and hear me. It's a great pleasure and honor to be giving a keynote here at the 20th HiPEAC. I feel like I have watched HiPEAC over the years from its start, and frankly, from my perch in the US, I've always been a little bit admiring and a little bit jealous of HiPEAC, the way it brings together European researchers across our topic area. So congratulations and happy 20th birthday. This talk, when I was given the invitation to come give a keynote, I said yes. Well, first I said, you do know I gave a keynote a few years back, and they said yes. So then with that knowledge, I said yes again. And it became clear that I was going to be giving this keynote on a day that's somewhat noteworthy for America. And, and so I started thinking. So there's two things about today. So first of all, we have a presidential inauguration. And at the time I said yes to this keynote, we didn't know who was going to be inaugurated today, but it seemed clear that something would be happening today. The second thing about today is that we celebrate Martin Luther King's birthday in the US as a federal holiday and as a day of service. So Martin Luther King was obviously an important leader in the US civil rights movement, but he's also known as someone who committed himself to public service, and so it's typically celebrated as a day of service in the US. And so that got me thinking about how we operate as a research community. Often architects, we're down under the abstraction layers, and so in a world where everyone's talking about AI's impact, blah, 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 we sometimes can kind of burrow in and let all of that sort of public-facing stuff pass us by. And so today is sort of a thought experiment. It's a different kind of talk. And really, I don't claim to know the answers. I claim to have a lot of questions about how we might be more visible in taking on challenges of real societal need and impact. So I hope you have some ideas along the way, because I think the world needs a lot more of our efforts in these regards. So with that, here we go. So I think I'll start by just sort of stating the obvious. There's an awful lot of things that need fixing in the world today. Here are a few. The climate change issue is a big and broad one. Food security globally is a big one. Trust in information obviously is huge in today's world, and broadening and making more equitable the access to economic opportunity. And in fact, the UN has a set of Sustainable Development Goals, or SDGs, that span across all these topic areas. And if you look at these SDGs, you'll never see the word computer. I think you sort of see access to information or internet access, but not really computers per se. You certainly don't see computer architecture there. But we know, people in this room know, that we contribute to all of these, right? Because you don't get very far in any of these without access to high performance, reliable computation. And so the question for today, or the conversation I wanted to try to start today, is about how might we better connect our technical work to impact on our societal goals. So basically recognizing we're not just computer architects, but we're citizens of the world, and what can we do about it? So I'm going to zoom in on three grand challenges here. One is about trustworthy computing. How best might we provide trustworthy and meaningful access to compute and to information in the world today? The second one is about climate and sustainability. And the third one is about people. How can we motivate entire local as well as technical topical communities to work with us, and how might we be more inclusive in that work? So these are going to be a mix of my own research group's work, but also experiences that I had through my 4 years that you heard about at the National Science Foundation, where I was kind of up-leveling to all of computing and up-leveling to thinking about sort of national opportunities in that case for these topics. So first, trustworthy computing. And let's just be honest with ourselves. From the start, computing hasn't really been trustworthy. Does anyone know what this is a picture of? So this is a picture out of Grace Murray Hopper's logbook. So she was working on one of the early computers in the 1950s. It was a computer that was based not on transistors, but based on relay circuits, so mechanical switching circuits. A moth got caught in one of the mechanical switching circuits. She writes it down. There's a bug in the computer. And that is how we got the term computer bug. And it has lived to today. So we've always had issues with trustworthy computing, but we're in a different place now than we've ever been. There's both trustworthy hardware and software systems, and there's trustworthy information. Let's talk about that trustworthy hardware, software, and systems a bit more. This is a graph that we all see a lot in our community. Decades of Moore's law scaling, in this case, drawn from 1970 to the present across different metrics. And you can see the number of transistors. It continues on that Moore's law scaling curve. Y-axis is obviously powers of 10, x-axis being years. So this is where we've been. We've seen this all a million times before. I want to draw it as two different chapters. So if you look at this part of the graph, basically that's the part of the graph where we had a stable programmer interface. So transistors were scaling, single thread performance was scaling. Under the covers, we as architects could do all kinds of wonderful things, out of order, superscalar, cache memories, and so forth. It was all scaling. And the hardware-software interface, that instruction set architecture, stayed stable. And so this is where we really had that sort of performance scaling curve at its most, I would say, accessible and most reliable. What happened more recently is that as single thread performance leveled off, as power became the limit, we had to switch first to increasing the number of logical cores, which you can see in the bottom set of black dots, and also switching to heterogeneous accelerators rather than sort of homogeneous parallelism. In the process, we lost API stability. We're now programming to systems that are very different than the sort of free performance scaling we had back 15 years ago or more. Today, every time an implementation changes, something about our software ought to change in order to get better performance. And if that's the case, then we've lost a lot of what computer architecture was originally coined to create. And so here's another image from the Wayback Machine. In 1994, Amdahl, Blau, and Brooks from IBM published this paper on System 360. And the term computer architecture is down here in the footnote. So this is where the term computer architecture got coined. So literally the same year that Moore's law is being sketched, this term is being coined. And why did IBM do it? I think you all know the answer. IBM wanted to be able to have one piece of software that ran on many different implementations. We've lost a bit of that over the past 10 years when we've adopted heterogeneity for power efficiency and for scaling reasons. And so now here we are. Across devices, we have massive heterogeneity, right? There's thousands of distinct Android devices. There's even more diversity in the IoT space. But then we have this heterogeneity on chip as well, dozens of ISAs on chip. So the idea that we have one ISA, no way. We have dozens of ISAs on these chips, CPUs, GPUs, radio baseband processors, and so forth. And we have fast changing heterogeneity where actually the mix of devices that we see, even on sort of the same vendor's chip, is changing from year to year, making it, I would argue, almost impossible for robust software to keep up. And so to me, there's all kinds of trustworthy information, trustworthy computing challenges, but to me, we have like a serious one right in our own neighborhood, right in our own yard. So I wanted to talk a little bit about one vignette from my research group where we tried to go after this problem. So over the past 10 years or so, we developed a set of tools that we came to refer to as the check suite. And it is an ecosystem that grew over time across this familiar stack. So it started with a paper called HiPEAC back in Micro 2014 with a simple goal. So the idea of HiPEAC was, can we check that a given microarchitecture correctly implements the ordering promises that that instruction set architecture has asked for? But then we realized that's just the beginning. We actually need to check from high-level language to architecture to microarchitecture. We need to check from microarchitecture to Verilog or sort of real RTL implementations and so forth. So we built up this stack that spanned different layers. And we also moved out into to other security issues that I'll talk about later. Across all of these tools, the idea that we rested our approach on was axiomatic specifications leading to what we called happens before graphs. And so anyone who's ever written or used an architecture simulator knows how many different out-of-order little intricacies there are in our implementations today. And so the idea of happens before graphs is a way of formally specifying what should happen before something else in any of our implementations. That is sort of a baseline plea for like order and correctness in a very complicated world. So what is a happens before graph? So these axiomatic specifications just basically say, in any correct implementation, A should happen before B. And maybe there's another rule in the rule book that says that B should happen before C. And maybe elsewhere in the rule book, there's another rule that says that C should happen before A. Now, the tools, all of these tools, basically take all the rules in the rule book and form all the possible graphs. Or at least conceptually, they form all the possible graphs. I'll talk a little bit about how we keep this tractable. So if A happens before B, and B happens before C, and C happens before A, then you can look at that and you can say, that's a cycle. That would say that A has to happen before itself. That's physically impossible, and therefore it will never be seen in a real implementation. Basically, we can check happens before graphs via sort of efficient SMT solvers, and we can say, if we see a cycle, that's an event sequence that cannot happen. If we see anything acyclic, that scenario is actually observable in this implementation. And we have to decide for the observable things, are we worried about them being observable or not? So do any of these observable event sequences lead to something that's problematic? So I've managed to get through this slide without saying a word that strikes fear into everyone's heart, but it's coming on the next slide. Consistency models, memory consistency models. When my student came to me and said, we should study memory consistency, I said, you know, you're bringing back a word that brought trauma to me as a PhD student when I was part of the research group that looked at relaxed consistency models in the 1990s. And then I realized actually by talking to people that essentially every professor like does a sort of moment of meditation before they go into their lecture where they try to teach consistency models to their students. We hate consistency models. But what I told my student when he said, this is Dan Lustig now at NVIDIA doing consistency models for them. When I told Dan that he wanted to do consistency and verification of it, I said, well, if we can automate it, I'm in. If we can't automate it, I'm out because it's too traumatic. So this is about, at first, about verifying memory consistency. And so if you go back to the beginning, memory consistency came from Lamport. He won the Turing Award for it about 5 years ago. And sequential consistency, that we can all handle. That's not too traumatic. It basically says the memory operations of each processor appear in program order. The memory operations of all processors, there has to be some agreed upon global sequential order that we can look at and see. And so for this simple two-thread program on the left, there's the 6 legal executions on the right. No biggie. That would be fine. But that's not where this story ends. That's 1979. So we realized, hey, the minute you have a write buffer, forget all the other stuff we do in processors, the minute you have a write buffer, you can't be sequentially consistent anymore, because a write buffer means that the local processor is seeing writes in a different order than the other processors, so that notion of a globally agreed upon order just went out the window. So Intel came up with total store order memory consistency as one of the things that they were going to hang their hat on. That's a little bit longer, but gosh, at least the basics of it still fit on one page. But it got more and more and more complicated. And so now when I teach my students about consistency models, I admit one of the kind of great shames, I think, of where we are in computer systems right now, which is memory consistency models are the specification of what value will be returned when your program does a load. And so that should be a solved problem by now, but it isn't. It's really important to specify it and verify it, and we haven't been doing a super awesome job on being able to specify and verify this across the different layers. So let's dig in a little more. So what are these happens before graphs that I mentioned? I had that A to B to C sequence on a slide a few slides ago, but here's kind of how we build it out for that first level of checking microarchitecture against architecture. Here's a tiny little program that we have, a so-called litmus test, and here's a fairly simple implementation, fetch, decode, execute, memory, write back. I just taught a class for third-year undergrads at Princeton, where this is kind of where we are in our understanding of pipelines. It has a store buffer, though, so it can't be sequentially consistent. So we can check things about whether this particular piece of code has certain outcomes that are observable or not observable. We create a set of microarchitecture level stages, and we create a set of graphs that indicate what is known to happen in order based on something very specific and local about the implementation, like, hey, one instructions decode stage will happen before the next instructions decode stage and so forth. And then we can have other parts of the happens before graph that are more dependent on the memory hierarchy. So from something like this, we can create, what we ended up creating was a domain-specific language that lets us set out the rule book for a pipeline. What happens in order, what happens out of order. So for example, an axiom that the execute stage is in order, a set of axioms that have to do with what edges exist in a graph. From that, we can enumerate, quote unquote, all possible executions. We don't actually do the sort of exponential enumeration, but rather we order this through different structured orders of the graph so that we can handle cases in aggregate. But effectively, we have a comprehensive way to assess all the possible microarchitecture happens before graphs and decide which are cyclic or not. And if this looks bad to you, let me introduce you to this. So we don't just stop with simple pipelines and kind of the assembly language instructions. We started thinking about things like, oh my gosh, what about when we have to do virtual to physical page translations? In those cases, the page table walker is doing memory references effectively under the covers that end up being what we call ghost instructions, memory references to the page table that need to be ordered correctly against user-level memory references and that need to be verified as well. So this is a happens before graph that was generated by one of our more comprehensive tools that also covers virtual to physical page translation. So I think we probably all at some point in an operating systems class learned about the idea that when we write to a page in virtual memory, a dirty bit gets set, and then when that page gets evicted out of virtual memory, we better write that page back to disk because something about it has changed. Well, this elaborate verification is part of how we can verify for things like, did those dirty bits get set in the correct order? Because if those dirty bits get set late, we'll end up evicting a page thinking it's clean and never write those bits back. Guess what? We found that happening in an operating system. So these are not sort of hypotheticals. These are real things that are happening in real systems. And when I started talking to companies about how they verified for those real things, the answer was often, we get the right people in the room and we talk them through. And that reminded me a little too much of the relaxed consistency conversations that I remembered from grad school. And again, back to my deal with my grad student, we needed to be able to do this automatically. So we created this whole framework for verifying this automatically for correctness, for reliability, for the ability to catch these errors much earlier in systems design during the architecture process, because if you wait and verify them when you have Verilog, it's kind of too late. You're often way deep in a design process. It's very expensive to back out of design decisions at that point. It's much easier if we can do this at the architecture level, and it's much better if we can arm architects with automated tools to do this automatically. So we came up with tools. They check for cycles in a graph like this automatically, so you don't have to stare at this graph, and they do it fairly tractably. In about an hour, you can verify some of the major systems that we develop today. And I'll talk more about the outcomes of this verification work in a second, but I wanted to take the next step, which is to a different kind of trustworthy. And in particular, this is the shift over to computer security. So in 2017 or so, we were pushing a little deeper on these tools, and we realized that there's security aspects to these ordering verifications as well. And for computer security, kind of like for these reliability and verification problems, we wanted to see what we could study automatically rather than thinking through. So if you think about an exploit like Spectre or Meltdown that got a lot of news a few years back, really the way that's portrayed in the news, the way a lot of us come to understand it is someone was thinking hard and came up with like a weird ordering and then demonstrated it. And so we wanted to say, like, how much of that can be sort of automatically figured out or synthesized and then automatically protected against. So we came up with this wish list. We'd like to be able to specify a system to study. We'd like to be able to specify a fairly abstract, high-level attack, quote-unquote, pattern. And then we'd like to be able to either output all the synthesized ways to do that attack on this system or determine that none are possible. And so if you look at those steps, hey, they look a lot like what we were doing for the memory ordering verification. Formal specification, something that we're looking to see whether it's observable or not, and then see what happens. So what we did is we actually developed a tool to do exactly this based on the microarchitectural happens before graphs, the mu-HB graphs from the previous slides. The results are that 2 weeks after the Spectre and Meltdown news broke, with those vulnerabilities being exposed, we were able to use our tool to synthesize those specific exploits, as well as several variants that were also being reported in those weeks, as well as 2 new and distinct exploits that we reported through the CVE process. So the way this works in a little more pictures is we take that same sort of microarchitectural specification as ordering axioms from the memory consistency work, and we add to it the ability to show a pattern. And I don't know if these 3 red dots sort of signify anything to you, but this is a way to abstractly represent what are called the prime and probe attacks that Spectre is based on. So basically executing something and then having items that are sort of live in the store buffer and the cache. And so putting this into the tool that came to be called Checkmate, you enumerate all the possible execution graphs that have that red pattern as part of them, and each of those represents a possible exploit on your system. So if you can sort of represent in the abstract the different prime and probe attacks you're worried about, you can verify your system early at architecture time against those types of attacks. So where did we get with all of this? So on the correctness results, what the tools have found bugs in so far is we started close to home. We found a bug in Gem 5, not so surprising, but that gave us the sense that we were on the right track. We found a bug in a cache coherence paper that had a proof of correctness that wasn't quite there. We worked with the authors to correct it. We found bugs in commercial processors that were in the design process. IBM was kind enough to let us visit for a morning and use some of the different compilers, and we were able to find bugs, consistency bugs, in their compilers when they went from minus 0 optimization level to 02 to 04. And this is all to indicate, first of all, that in live commercial systems, there's an awful lot of correctness issues still to catch. And second of all, to indicate that these issues are hard to sort out because they cross different levels. And so the ability to have tools that cross different levels is important. So that brings me to a few other things. So when we were doing this work, the RISC-V instruction set architecture specification was in draft form. And in particular, its memory consistency model was in draft form. We took a look at the consistency model relative to the architecture, and we found that the consistency model would not allow for the correct compilation of C11 programs. So basically, there were cases where the C compiler simply could not correctly compile to RISC-V. And so that was a case where we flagged the error, and through the RISC-V study group process, we were able to work on changing the memory model specification to fix that error. And the result is that now RISC-V has an extremely solid memory consistency model with a formal verification backing it up. And at the same time, another outcome of those discussions was, hey, this C language specification that caused part of the issue there is kind of a crazy thing to ask compilers to be able to do. And so actually the C11 standards committees have been discussing adjusting the memory model in reaction to this work as well. So that's on the correctness side. On the security side, as I said, we automatically synthesized exploit code templates for hardware aware vulnerabilities like Spectre and Meltdown. We automatically synthesized Spectre and Meltdown. And then we synthesized these different variants as well, including identifying 2 that were based on cache invalidations, whereas Spectre and Meltdown are based on speculative cache pollution. So what are some of the lessons learned? I think going to a formal axiomatic approach was a big lesson learned. I'm not a formal person. I came through architecture doing fairly empirical work, but this chain of events proved to me that formalism buys us something, and what we need to work on as a community is how can we create tools that make it easier to use formal techniques. Second was early stage analysis, the ability to pull this kind of analysis into the architecture process rather than waiting for the very end. And over the years, so like when I think back to when I started working on power efficient computing, there was the thing I kept hearing was that architects shouldn't do power. We should let the VLSI people worry about power. And what the folks like myself and others who were working on power 20, 30 years ago said was, no, we need to do it because there's more leverage early on. And so now what I'm saying is similarly for correctness and security, there's more leverage if we do it early on, so we have to pull this stuff into architecture. We can't wait for RTL. The last thing is the ability to span software, operating systems, and hardware. There's too much of our world that's sort of segmented. We need to be able to reach up and sort of look at that full stack approach, or we would never have been able to find bugs. For example, the C11 to RISC-V memory model bug wouldn't have happened if we had just looked at the lower level. So that's one kind of deep dive. What are some other sort of broader view? If you look over the years, there have been some interesting papers in our own community. For example, Hardware Bugs and Security from Micro 2018, Cynthia Sturton. Caroline Triple, who's my student who did the Spectre and Meltdown work, is now faculty at Stanford. She looks at protecting against silent data corruption as a variant of this. Two interesting things over the past couple years have to do with GPUs and memory model testing and GPU local memory security. If you haven't heard of this work, I'll give you a pointer. It's pretty interesting. So Tyler Sorensen, who was a postdoc in my group and is now faculty at UC Santa Cruz on the west coast of the US, recognized recently that there's a way by which many GPUs leak information through their local memories so that one user of a GPU can see and recreate the ChatGPT dialogue stream from the previous user of a GPU. So if you're asking ChatGPT whatever personal questions you're asking, keep that in mind. There's a whole set of different vendor GPUs that were found to be vulnerable of this. This was released just about 6 months ago. Okay, in the interest of time, I'm gonna skip a little bit on the AI stack. So in terms of this example and expanding societal impact, here are some sort of broader questions and ideas. So there's a reporting process for bugs and vulnerability, and I know that until we had these Spectre Prime and Meltdown Prime bugs in our, coming out of our tools, I personally, in my 30 or 40 years of research experience, had never had to use a CVE reporting process. I had no idea how to do it. So A, you should use it, and B, we should help our students, who are architects, not security experts necessarily, understand it as part of how they grow as researchers and understand it as well as they understand the paper publication process. There should be collaboration across topical boundaries because a lot of these kinds of trust and security issues aren't going to be very localized to specifically the architecture community. They reach across. And then there's an ethics component of this, and I feel strongly that we should be teaching our students as much about ethics as about other core topics. We should teach our students about ethics in essentially every class, not just sort of put it on the side as an ethics class. And while I sort of wrote this part of the slide with a lot of an eye towards the students, I will say, in America we have this expression, teaching old dogs new tricks. So faculty need help learning these issues too. I certainly was learning as I go with some of this. I didn't know sort of how responsible disclosure worked until I had something to responsibly disclose. And so understanding how we can improve sort of a faculty understanding of this is important. Okay, so that's one. I wanted to move on to the next couple, which we'll do in not quite as much detail, but this one is about climate and sustainability. And it's a two-way street. So one way is how might we use computing to help improve our plans for a sustainable future? And the second thing is, like, how might we make computing itself more sustainable? And it goes both directions. The more we can actually use computing for logistics and so forth, we can save the carbon footprint of air and truck deliveries of products and so forth. But I'm going to focus more on the second one, of making computing itself more sustainable. So this is presumably well known to many of you, but modern data centers dissipate massive amounts of power, similar to sort of city-scale dissipation. And AI is driving higher usage of existing data centers and increasing the pace of building new ones. So here's some information from Meta. Here's the good news first. So the good news is that sort of over the trend from 2010 to 2018, what we saw was a large increase in the instances of so compute instances within data centers, and actually a more modest increase in the electricity usage of them. So this is the good news in the sense that we were able over that time period to build, to scale up capacity for compute faster than we scaled up power. So that seems like a good thing with two caveats. First caveat is, that data ends in 2018. A lot has happened since 2018, you might have noticed. The second caveat is that the demand growth over that last chunk of time means that aggregate electric usage is growing fast. And so what this curve shows is 2017 to present-ish. This is the Meta curve in red, the Microsoft curve in yellow, and the Google curve in blue. This is the scaling of electricity usage normalized to where Meta was in 2017. So huge scaling, and let's remember that 2022 is sort of pre-ChatGPT. So the past 3 years of big boom are not accounted for in these scaling curves. So there's an awful lot we need to attend to. So this is not actually that new. Here's a trip in the Wayback Machine. James Hamilton from then Amazon gave a keynote at ISCA in 2009 on data center power usage. And he gave some very helpful real numbers for sort of facilities and servers and so forth. It helped ignite a lot of interest across our field in data center energy optimizations. So just as one example from the Wayback Machine, Riccardo Bianchini and myself and some of our colleagues worked on framing of these problems. This is 2009, 2010, where we came up with optimization scenarios for how might we route internet requests to better use green energy where it was available. So if you had one data center over here that was 70% powered by green energy and another data center over here that's 70% powered by quote unquote brown energy, how might we get more requests to the green energy data center without tanking performance in the process? So we had this notion of dynamic power measurement within the data center, and we had a notion of request distribution across data centers, and we had a way of planning formally on different timescales so that we could stay within these performance goals. Seemed like a good idea to us as academics, and we came up with some nice results. We said with perfect predictors, with a carbon market available to us, and with this simulated annealing-based optimization, we could get significant cost savings, significant brown energy savings, and so forth. So that was a while ago. So what's happened? What's happened is essentially request distribution still doesn't happen 15 years later. That's a shame. And we're sort of reassessing all of this with kind of a second wave of effort. I think one of the good things that's happened in this more recent second wave is the notion of studying not just electricity, but carbon footprint. And in that carbon footprint is both operational carbon footprint, the direct cost or emissions of powering the compute itself while it's in operation, but also embodied footprint being what does it cost to build these devices? And particularly for mobile and edge devices, that embodied footprint of fab is pretty large. Here's some examples of this embodied footprint issue. For Apple's end-to-end breakdown in 2019, manufacturing, that embodied footprint was a huge fraction of the overall footprint in their work. I think Apple is an extreme because of how much of their business is on the mobile side, but nonetheless, I think that's this notion of carbon footprint versus electricity and the notion of embodied carbon as well as operational carbon are ways in which the nuances have improved since those early sort of 2009, 2010 studies. Everything old is new again. Here's a paper from ISCA 24. I'm not an author on this paper, but actually Riccardo Bianchini, who was my co-author on that previous paper 15 years ago, was an author on this. He's now a VP at Microsoft working on Azure, working on these data centers at scale. And so what they looked at in this paper was how to build data centers, how to build cloud servers for lower carbon through things like reuse of different parts of a system. So it's nice to see the attention is still there, but I think the problems are more unsolved than solved right now. And in particular, I will say, I still don't see enough people acknowledging that just request distribution might be viable. I feel like in many cases that's sort of dispensed with pretty early on in discussions. Slightly more good news is that a carbon-aware research community is forming. So in the US, this announcement a few months ago, NSF put $36 million into 3 major computing projects that all have to do with this carbon footprint and energy demand issue. When I was looking around, I found that actually Europe has an even larger number devoted to investments in the Green New Deal, I think it's called. So it's heartening to see it happening. In terms of this push to sort of broader societal impact, there are tools available. I feel like as architects, one way that we learn about different issues is we, faculty and students, having tools that help us sort of explore a space. And so there are architectural carbon tools coming out of some of the early researchers. And I know I've got a set of students back home that I'm trying to get interested in using these tools because it's how I and they will learn about what are the design opportunities there. So increasing awareness and also learning. I think we have opportunities to look differently at specialization with this in mind, and to consider sort of the energy sources along with energy dissipation when we do our work. So this is kind of sort of recognizing how our work that we do every day connects to this bigger issue of sustainability. So with that, I wanted to get to the third one, the people one, and how can we sort of change what we're doing in terms of inclusiveness and people. I think I'm going to frame this around CS and AI more broadly than architecture. So I think there's different aspects to the inclusion problem. So one aspect of it is inclusion in our education and research. Another aspect is inclusion in the workforce overall. And a third and growing aspect for us as a broad technical community is where there's AI training data and models, we need to work as a broad community to make sure that all the people on Earth are sort of usefully and inclusively in that data, or else the models that we're generating as a community, as a broad computing community, won't be reflective of Earth as a whole. When I was an assistant professor, Bill Wolf, who comes out of our community, Bill Wolf coined the term memory wall way back when, but Bill Wolf was also president of the US National Academy of Engineering in the 1990s, and he said this quote, and I can say that as a pre-tenure assistant professor, having the president of the US National Academy say this was extraordinary to me, and it actually helped me change the conversation at my university about what diversity means. So what he said was, without diversity, the life experiences we bring to an engineering problem are limited, and as a consequence, we may not find the best engineering solution. We may not find the elegant engineering solution. We pay a price and opportunity cost. So we pay a price by having designs we haven't thought of and solutions not produced. And so to me, this is extraordinary because it brings it not to a question of being fair to the people you're leaving out, but being open to the good ideas that you're missing out on. And so I hope that this kind of quote will help motivate us to keep working towards inclusion in different parts of our space. Here's a few sort of concrete examples of that that I've worked on over the past few years. So number one, we were actually talking about this at dinner last night. AI is driving our field. It's driving computing as a whole. It's also driving computer architecture in a lot of ways. And there's a real question, who can actually meaningfully impact AI right now, AI research, AI innovation right now? I would argue that it's increasingly concentrated in a few companies, and it's harder and harder for students and academics to have access. And that's a problem. And it's not just a problem for your quote-unquote AI colleagues, it's a problem for us in architecture because we aren't able to influence things as we should. And so there's design opportunities that the world is missing out on because we're not included. I don't know if this is the full solution, but one solution that I worked on while at NSF, and I'm happy to see continuing to sort of roll and expand, is the US set up a task force called the National AI Research Resource Task Force that discussed ways to democratize access to AI resources at scale. The pilot was launched a year ago, January. You can check out nairpilot.org. It's about basically making available US supercomputing resources and data resources for broad public use, some of which have sort of international access components to them. So check that out. The cynics will say, sorry, but those supercomputers aren't big enough. They aren't a full solution. But I think there is still hope that we need to push on this direction. And the data resources that are being released, I think, are helpful. So for example, the Allen Institute for Artificial Intelligence in the US released some of their data and models towards this pilot. At an even more local level, I've been working within, so Princeton University is in the state of New Jersey in the US, and at the state level, so the state of New Jersey has launched an AI hub, and one of the key aspects of that is improving access to AI education. So I was a co-convener of a curriculum sharing workshop a couple months ago on sort of how can all of the universities in the state of New Jersey work together on this problem. The funny thing is, we envisioned this as a bunch of computer nerds coming together and figuring out, oh, I can put in my junior level AI class if you put in your sort of first year introduction to AI class. We really thought about it as a nuts and bolts thing. The governor of our state found out about it and said, I want to be there too. And so this is a picture of our governor kicking off this convening. I think that gives you a sense that there's both sort of political will to push on this, as well as a need and a desire amongst our own community to push on this. So I think these are examples of like getting into the picture. I think that if architects are in the picture on things like AI education, AI curriculum sharing, we're likely to create a curriculum that actually acknowledges the degree to which hardware innovations have driven AI, not just some algorithmic and data stuff up top. Okay. Other opportunities for action. I gave this talk in November to a US audience, and so when I started thinking about this talk for today, I was like, oh my gosh, I know the US side of this picture better than I know the European side of this picture. So I'm gonna step through some slides. If I'm missing stuff on the European side, I'd welcome hearing about it during the Q&A so that everyone in the room can know what else is out there. But here's a few things that you can do, that we can sort of make access of. So research funding, I think one of the things that I wanted to get the word out about, so for the 4 years that I was at the National Science Foundation, I was really struck by the attention to funding for international research collaborations. And frankly, before I got to NSF, I'd been unaware of a lot of it. So here are some examples. There is a fairly large multilateral program called CRCNS. It's on computational neuroscience, and you're going to say, I'm an architect, I'm not a computational neuroscientist. But actually it gets into neuromorphic computing and other things, so it's a two-way street between the brain and computers. And it includes, by design, funding for researchers from the US, and that includes our NSF, but also our National Institutes of Health, our Department of Energy, other federal agencies. So it's several US agencies. It's one agency from Spain. I'm going to say the acronyms and probably the wrong pronunciation of the acronyms, but AEI. In France, it's the ANR, so the French analog to NSF. Germany, Israel, and Japan. So this is one example. Actually, there's a whole web page within the directorate that I used to lead within that directorate's website for the different international partnerships. You can see some of what's available there. In general, the model that the US NSF has used for international partnerships has been that we put in the money for the US-based researchers, regardless of citizenship, just US-based researchers. And then the collaborating country provides the budget for that country's based researchers. The proposal gets reviewed as a single proposal, and if funded, the 2 buckets of funding go out to the 2 sides. So that has worked across a range of countries, including a bunch that presumably are in the room here based on what Kun's graph of attendance looked like. So that's one. So there is funding for international collaborations, and that may be a way of kind of broadening how we work together. The other thing I will say is I feel like as a community, we don't respond to policy opportunities as often as we might. So the US government and the EU governments and so forth are often putting out requests for information, RFIs, or other opportunities to comment on policy. And I feel like in many cases, there's some sort of policy people within our community that are doing those replies, but the typical architect doesn't step away from our simulator and go and answer these replies. And we probably should, because I think one of the things I worry about with a lot of the policy discussions is they stay at the software layer, they stay sort of a higher level veneer, and they don't talk about the ways in which hardware design trends are really shaping some of these issues. So this is just one screenshot of an RFI that's lapsed, but there's actually a bunch of these live most of the time. And for different countries or for different entities, there's different places that you can track them. ACM has a US Tech Policy Committee and a corresponding Europe Tech Policy Committee, so that's another place where you can get involved. You can respond to these kinds of requests as a group. I think I just got an email overnight or maybe 2 days ago that the Europe Tech Policy Committee has done a response on some of the most recent European AI legislation, so that's great. But again, I don't know how many architects are in the room when those things get written up. This I found yesterday. I don't know, does anyone use this? There's something called the Have Your Say, and you can go in and write comments about all kinds of EU rules, which is sort of fascinating. I couldn't find any live about hardware, but I did find some live about AI and I think medical devices and so forth. In the US, we have opportunities to do fellowships to go into different government settings. About 9 years ago, I did one of the Jefferson Science Fellowships, which is one of the boxes I included here. Jefferson Science Fellowship Program was a program that was started about 20 years ago with the goal of getting science and engineering folks into diplomacy settings to be technical explainers. And so because there's an awful lot of international discussions right now that are focusing on technology issues, it would be really nice if someone in the room understood those technology issues in a deep way. And so the idea of JSF's, Jefferson Science Fellowships, was to have some technical explainers in these science policy discussions. That was a very rewarding year. And then another thing in the US is the ability to be what's called a rotator into the different funding agencies. So I went for 4 years to lead a directorate at NSF, but there are rotators at other levels at NSF, and also our Defense Department research agency, DARPA, also has this notion of rotators. So then when I was preparing for this talk, I said, I wonder if there's a corresponding European analogy to these rotators. So I was like, I was ready to Google, but I was also thinking back when I was at NSF, and I was meeting people from other countries through these international collaboration discussions, I would meet people who were both, say, from the Italian embassy, but also associated with the university. And so a bit of Googling turned up, for example, this. So this is from one of the Italian websites, and it does talk about the fact that there are folks who act as science and technology attachés who come from universities. So I'm not familiar with how this works, and I'm not familiar with how much of this is EU level versus country by country, but it does seem to be the case that just as I was able to go on leave from Princeton and rotate into a government position, I think there are analogous opportunities on the European side. Correct me if I'm wrong. So I will say, in the beginnings of a conclusion, I've been a faculty member at Princeton for 30 years. But actually, if you count my Jefferson Science Fellowship year and my 4 years at NSF, I've spent 5 of the last 10 years in Washington, D.C., and I have, in the process, served the past 3 presidential administrations, so both of our major parties. Obviously, I might vote one way, but what I found was it was possible and helpful to be in government service, regardless of whether I voted for particular people or not. I think it's really important to figure out ways that we can engage in that way, because I think the world needs us and our explanations more now than ever. At the end of my Jefferson Science Fellowship in 2017, I wrote a piece that ended up in CACM on science policy and service. I haven't updated it, so I learned a lot in the 4 years at NSF that are after this piece. But yeah, I'd welcome you to check it out if you're curious about how how a computer architect goes into some of these discussions and what I found most rewarding about it. There's certainly a notion of sort of up-leveling to things that are important to the world and to society that I found really rewarding. So I wanted today to start this conversation about connecting technical work to impact on societal goals. Like I said, it was not my normal kind of technical talk. I could have just geeked out for an hour on quantum computing, and that would have been fun too. But I did want to kind of raise these questions as questions, and I don't have all the answers, but I am fairly optimistic that we can find some. In terms of looking forward, here's some other things that maybe are happening at a granularity that's bigger than any one of us. So I think university departments, we're kind of weird. Like, computer science is the center of the universe as far as I can tell. So why are we just one department? We should be working across all kinds of departments, and we should be making sure that our tenure and promotion decisions at our universities are respectful of the kinds of collaboration that we most need to be doing right now. So I would hate for a tenure committee to say that one of you wasn't deep enough in your particular technical area because you were off changing the world. Industry, I worry that industry isn't as supportive of research both within its own company and externally out to academia as it once was. I appreciate the many, many sponsors of this event. More broadly, I do wonder about this question. And industry plays a strong role in tech translation and impact, so actually sort of up-leveling those ideas. Finally, professional societies. I have benefited a lot from different things that SIG-ARC and TCCA have done for the architecture community, but I do wonder if we need to be more in the mode of multiple SIGs working together in order to get publication scope broadened. So it's hard to do sustainability within a particular SIG. How might we broaden it out to really encompass sort of broad societal challenges? So thanks very much.